Chapter 9, Section 3 talks about states of matter that we're going to include in our balanced chemical equations. So this is an example here at the bottom how we would write those states of matter. You're probably already familiar with solids, liquids, and gases. S is solid, L is liquid, G is gas. So one that's probably not quite as familiar is aqueous, or AQ. And that means that you have actually taken a solid and dissolved it in water. So like in this equation down here, this is the equation for cellular respiration, shows you that glucose here is aqueous, so it can be dissolved in water, and that our oxygens are in the gas form, CO2 is in the gas form, and then water would be in the liquid form. So those states are written to the bottom right of each formula, and they're usually written as a subscript and in italics, and we also use them in lowercase letters and put parentheses around them. And this particular equation is also an exothermic reaction, which is important to remember. It's got energy as a product, so that means it's being released. If it were written with energy as a reactant, it would be an endothermic reaction. These are also some different conditions that you might see in a balanced chemical equation. Yield symbol, obviously you already know that one, that separates our products from our reactants. Equilibrium, which we'll focus on more a little bit later in the year, but that's a double arrow. So you get the reactants reacting to combine to form products, and then the products will recombine to form more reactants. So you have arrows pointing both directions. Some reactions will only occur with heat. So we would represent that by putting either this little triangle symbol above the arrow, or you could just simply write out heat. Some are so specific that you need to actually put the particular temperature. So you would specify the temperature that you would conduct that experiment at, or maybe also the pressure as well. So here we would have, that this equation would need to happen at 1 atm of pressure. The other thing you might see are catalysts, which will just be an element symbol. This one is palladium, so that's telling us that this reaction has a catalyst that helps it go quicker. It doesn't actually participate as a reactant or a product, and that's why it's just written above, or it may be written below the arrow. Some other things that our balanced equation will show us are relative proportions of our chemicals. So for the same equation, this cellular respiration one, this is the same as saying that we've got 1 mole of glucose combining with 6 moles of oxygen to make 6 moles of carbon dioxide and 6 moles of water. Those are all the different ratios that we are going to be using in some calculations here. So a mole ratio is just the conversion factor that's used to convert from one type of mole to another. So anytime you're trying to go from one substance to another, like using the oxygen here to find out how much carbon dioxide we could make, you're going to need to use a mole ratio. So to do that, you're going to compare the coefficients. So for this one, I just made up a value here. I said we have 3 moles of glucose, and I want to find out how many moles of CO2 that could produce. So I need the ratio between the glucose and the CO2, which is a 1:6 ratio. Those are just the coefficients. And I'm going to set up my conversion factor to cancel out my moles of glucose. So the glucose needs to go on the bottom, and the moles of CO2 would go on the top. So that way when I multiply across and divide by the bottom, that will cancel out the moles of glucose and give me the answer in moles of CO2. So if I have 3 moles of glucose, then that means that I could produce 18 moles of CO2. This is just another sample problem. So it says determine the number of moles of each product that would be formed given 16 moles of KClO3. So I already have my balanced equation, so that's done for me. So I'm going to start my calculation with my known information, which is the 16 moles of KClO3. Now I need to find out how much of each of these products that I could make. So that will be a separate equation, one for each one of those products. So the first ratio I'll be using will be from my moles of my reactant to moles of the first product, which is KCl. So it's a 2:2 ratio. So that's how I have it set up here. And I want the moles of my reactant on the bottom so that it will cancel out. So I'll multiply across, divide by the bottom, and that will give me my moles of the KCl that I could make. Now I'm also going to do the same thing with my other product because it asked for both. So in this one, still setting it up with my known information, but my ratio is going to be different. It's going to be my ratio that's between the reactant and the O2. So this time it's going to be 2:3. So I want my 3 moles of oxygen on the top and the 2 moles of KClO3 on the bottom. And when I multiply across, divide by the bottom, the moles KClO3 get canceled, and that'll tell me that I can make 24 moles of oxygen. Now the last part I could do is also calculate how much energy was given off, since that was a product as well. So in my balanced equation, it said that I could produce 78 kilojoules of energy for every 2 moles of KClO3 that I had. And that was just straight from the balanced equation. So that's the ratio that I'm going to use. It's still starting with the known information that said that I have 16 moles KClO3. My 78 kilojoules needs to go on top. 2 moles KClO3 needs to go on the bottom. So I'll take 16 times 78, divide by 2, and the mole units will cancel. And then total, I can find out that if I had 16 moles of my reactant, I could produce 624 kilojoules of energy. The last thing we're going to mention in this section is enthalpy. And enthalpy is represented by a delta H. This is the Greek delta sign. And it's just the total energy of a system. So how much energy is either being absorbed or released. So it's usually measured in either joules or kilojoules, since it is an energy value. Now, if a reaction is exothermic, then that means that it's going to have a negative delta H, which means that it's giving away its energy. For an endothermic reaction, you're going to have a positive delta H. So that means that energy is going to be added in order to have that reaction happen. So if I give you an equation and give you the enthalpy and say that it's a negative delta H, you should be able to tell me that it's an exothermic reaction. If I tell you it's a positive delta H, you should be able to tell me that it's an endothermic reaction.